probably taxable, which it shouldn't be, but or maybe it should be. I don't know.
Just asking. Didn't never seen T at the end of prices before. Okay.
Okay.
I'll just hit reply and say got it. Is that Ilya? No, that's someone else. Okay. A lot of background noise.
That was Richard joining there. And Richard is going to be joining us, Ray, to man the Ferroscope.
Okay.
And walk us through some of the slides that we're going to be looking at. All right, Marissa, I've got us set up live streaming. If you want to get us kicked off, we'll get into it.
I would love to get us kicked off. Hello, everyone. Welcome to another Grease Thief Thursday. Today, we'll be talking about analytical ferrography and taking a deeper examination. A deeper examination can determine abnormal components conditions. We have our speakers today. First, we have Rich. And Rich Forsbaugh is the president of MRG Labs. He has over 30 years of experience in the development of condition-based maintenance programs. He is certified in the International Council of Machinery Lubrication, ICML, as a machinery lubricant and engineer. He also has over 30 years of ferrography experience, part of which he was responsible for the design and the development of the Peach Bottom Oil Analysis Laboratory at Peach Bottom Nuclear Plant. He has also helped advance ASTM standards and is an active member of the ASTM for In-Service Lubricant Group. We also have a very, very special guest today. We have Mr. Ray Daly with Trico. And Ray has been performing research, manufacturing, sales, and marketing with ferrography for the past 30 years. He gives lectures worldwide for the Electrical Power Research Institute, Society of Automotive Engineers, National Lubrication Grease Institute, Joint Oil Analysis Program Conference, and Society of Maintenance and Reliability Professionals. He also does a lot of training courses, and in addition, he is the vice chair for the ASTM D2-96-5 for Conditioning Monitoring Group. He has published numerous technical papers and reports in the areas of lubricant and wear particle analysis. He also holds memberships in the STLE, ASTM, AFE, and American Society of Metals, and as the executive member of the SMRP. So together, they make a joint of 30 years of ferrography, or I'm sorry, 60 years of ferrography experience here to demonstrate today. So we are so lucky to have both of them here. Also on the slides, you will see later, we have Richard Janoski. He will be managing the slides in the demonstration. And Richard Janoski has been with MRG Labs since 2013 and currently serves as the lab manager for MRG Labs. Here at MRG, he works in the laboratory analyst grease. He works in the lab analyzing grease and oil samples. He also prepares data for customers and participates in the R&D projects. He is ICL certified in LLA2 and MLT1. And I will now pass over to Rich, who will take a deeper look at analytical ferrography.
Thanks, Marissa. And Ray, thanks for joining us today. It's pretty exciting for me. If I say I've got 30 years of experience, you have to have 30 plus, because you were the expert that got me started. And I do remember that back in 1989 when we took you into the basement of the nuclear power plant to an old bathroom and said, this is where we're going to do lubricant analysis. So we've come a long way since then, but it's great to team up again here, and I really value your input. I'll get us started here by giving a little bit of the background from our perspective on analytical ferrography and really talk about that specific to greases. But I'll start with some more general overview. What is ferrography? It allows us to look at contaminants and particulate that helps us determine what's happening from an asset perspective, from a wear perspective, and other mechanisms that generate particulate, including contamination. The benefits are that it does allow us to identify wear mechanisms. So we go beyond numerical values and trends to better understand what type of wear, what is the process that's causing that wear, how severe is it, and so forth. And wear, of course, is what we see when we get the interaction between contacting surfaces. There's some wear that we consider normal, but we definitely want to be in a position to analyze and to identify abnormal wear mechanisms. And we might see from that the reduced life of the component. We might see more vibration, more noise, and even poor performance in some cases. Some of the particulate depends on what is the mechanism that forms it, how it looks, how it appears, what kind of sizes it generally gets manufactured in or created in. And you can see you got different wear modes identified here: break-in wear, kind of normal or steady wear, pitting, scuffing. Different mechanisms that lead to that: abrasive wear mechanisms, cutting wear, fatigue and adhesion, and we lose lubricant films. And then we talk about the types of particles that they generate in terms of what we see under the microscope, what we take pictures of, and then we compare to libraries to say, this is what we have going on here. And we call these particles things like cutting wear particles and spherical particles, sliding wear, laminar, those types of things. And so we'll look at some examples here today. And so the setup here is, under the microscope allows us to see this. And the typical microscope you might be using today is going to have, a camera hooked right up to it so that we can put that right into an electronic kind of data communication network. We can create reports, email the pictures, share them back and forth. And today we're going to use that to our advantage to broadcast that live, the view of what an analyst like Ray or Richard Janoski is going to see when they sit down at the microscope. And it's going to be what we call a bichromatic microscope, meaning that it has two light sources. One light source comes up from underneath, and allows us to illuminate those particles that can transmit light. The other is a reflected light source that shines down on the particles and lets us see the metals and some of the other things that don't transmit that light. And so we can kind of play with those light sources. We can do things like use filters of certain types and better understand what kind of particles we're looking at. First, though, we have to create the slide, and the slide is created. It's a glass slide, and it's created over a magnetic field. So we use a magnetic field that's generated by two large permanent magnets that are separated by a thin separation of aluminum that creates this strong magnetic force, and that force creates a field that kind of comes up through the glass. So as we put oil, a combination of oil and a solvent together and flow them down across this slide, it's going to subject it to that magnetic force and arrange it and capture those particles in these specific lines. Now, why, how does that work? Well, the slide is not just a glass slide. It has a plastic-like material kind of painted on there. And when the solvent hits that, it softens it. So now when the magnetic force or just gravity pulls particles down to the surface of the slide, they kind of get embedded into that matrix. And then when things evaporate and dry out, they're held in place. They're fixed. In fact, we used to call the solvent, we would use a fixer, and it would just fix by first softening and then allowing it to evaporate and harden again, fix those on the slide, because otherwise you would take this off of there and you would sneeze and you would lose all those particles, right? So this is the way that we capture them in this specific arrangement. What's really nice about this is that the magnetic field allows us to see the size distribution of the particulate by catching and concentrating the larger magnetic or magnetically susceptible particles there at the beginning where the oil is first introduced, and then smaller particles as we move further away. It also has the effect of orienting the particles in these magnetic lines of force that run perpendicular to the flow. And so you see them get lined up if they are ferromagnetic. If they're not, they're random. They're randomly oriented, as well as making their way further down the slide before they actually get stuck to the surface. So very quickly, we can look at that arrangement and distinguish between ferrous and non-ferrous particles, see the size distribution of the ferrous particles, and so on. And Ray, you can feel free to add anything or throw in some other comments as we go through here.
I was going to add that there's got to be an air gap between the slide and the magnet. It doesn't sit flat on the magnetic field, or else the particles will basically clump up on each other at the entry of the lubricant coming down with the solution mixed in with it. So that's why you have to have somewhat of an air gap tilt of the slide coming down towards the drain area. So just wanted to add that.
So you're actually, as you go further down, the field strength actually increases a little bit as you get closer to the slide, right?
Yeah, that is correct. So,
and this is something that was determined over time by guys like Vern Westcott to really optimize this process.
Yep, Rod Bowen, Vernon Westcott, and Dan Anderson. They're the ones that was instrumental in putting the design aspect of this machine together. So,
I think a lot of people take that for granted. They just say, "Hey, I'm going to throw, this piece of glass onto a magnet and everything happens." And it's really much more nuanced than that and very deliberate, right? In this design. It is
deliberate. The flow of the fluid is very deliberate too. That's why you just can't pump a sample on there and expect it to just create a pattern of this nature. So it's a control fluid usage of putting onto the slide itself. So, and has a certain gap and a certain Gauss that's being used in the on the magnetic field too. So
I imagine if you would change the magnet in some way, that it would change your expected patterns for the same kind of particle distribution, right?
That is correct. So if you start doing that, all of a sudden you can't compare apples to apples anymore. So that's where that comes into play.
Yeah, you and I were looking online at a message board the other day, and someone had some photographs of ferrography, and I was kind of confused at first, and you mentioned that maybe the slide had been taken off early because of
Yeah.
the pattern, and then we found out it was a completely different device, right?
Correct. It was the rotary particle depositor type device, which basically does not need a non-wetting barrier, needs just half the slide, but it has to be held on by a suction cup on over to the magnet, circular magnet. And then what you do is it's almost like a bicycle spoke wheel. The oil comes into the center, and then centrifugal forces basically pushes it out to the outside. And then what happens is the ferrous debris gets caught into the ring magnet area. And then from there, you have to make an assessment, which is the area of the largest particles versus the smallest particles. Tougher or more difficult to capture the non-ferrous debris because the centrifugal forces of that machine will allow this to go out. Now, what happens is that device was specifically, it originated from Swansea University, and that device specifically was designed for the coal industry in their lubricants because they have a lot of coal dust. And so by using the centrifugal force, that allows the dust to go away, and then the particles will be sitting right there that you want to basically analyze a long hauler or anything that would underground mining or surface mining. So as you know, in England and Scotland and Wales, they did a lot of coal mining activity. So that's why that the design was there in place.
Well, it does create a different view,
yes,
a different look to the particles, and I kind of mentioned that I think I'd have to recalibrate my head to get used to that because of just being familiar with this deposition pattern and what to expect and what it means.
Yeah, we were working with I don't know if anybody knows this name, but I'm blasting names from the past. Mervyn Jones was the guy that was involved with the Swansea University, and Brian Roylance, and he introduced me to those particular product lines, and we were interested in it, but saw that it didn't gravitate towards the non-ferrous debris in certain areas for us. If we didn't have a big interest in the coal industry, I put it to you that way, in the mining industry, to say.
Well, that's certainly not as big as it once was either now today either.
That's
so
correct.
So thanks, Ray. And if we do this right and we get this prepared, and in that discussion we also said you got to be careful you don't pull the slide too quick. You still have some unevaporated solvent on there. I'd actually rearrange the particles a little bit, and it looks kind of squirrely, but you get it done right, and it creates this nice distribution where you can kind of go through very methodically. And we'll see Richard do some of that in a moment, look through the slide. Now, Ray, at our lab, we've gotten a lot more involved in grease analysis, but my first grease analysis was done with you when you came and visited our plant. And at that time, back in the late 80s, some folks were doing grease analysis there too. And I recall that method involved getting some small glass beads and putting them into the vial, having a special separate solvent. I think that would be hard to use today because of some of the things that were in there that maybe really not looked on too favorably today in terms of solvent use. But the idea there was to really go to work on that grease to try to break up that thickener structure and allow that to kind of get out of the way of the particles that we were interested in.
That is correct. It was masking what we wanted to look at. And so what happens there is we tried everything we could to break down the grease to a liquid format. And as you said, we use certain chemicals. And then from there, we use some of the glass beads to help separate what's going on. And then take that specific grease with the mixture and then place that into filtered oil, and then run the filtered oil with the grease mixture in it simultaneously to be able to make the analytical slide that you talked about. One of the things we did that for was the if anybody remembers, the Huey helicopter for the U.S. Army in Iran had some issues where the dust is where the dust, when it gets near the ground, goes right back into the yoke and bearing assembly. And because it was oil lubricated, it would just trash that particular unit. So what happens now is they process we use a grease process of extracting the debris, looking at it, and then being able to see how that assembly is doing. But in the meantime, what they've done is a fix. If you notice, a lot of those helicopters now have a circular cone right on top of that area where that effect does not cause any problems anymore. So literally that helped fix what's going on with regards to the engineering aspect of the helicopter. So, but yeah, it was a good reminder back in the old days of almost 30 years ago, what we were doing with grease analysis. So.
Oh yeah, and just fast forward, just within the past year, we've been doing some other helicopter grease analysis studies from those swash plate bearings, and we've approached it a little bit differently, and that's what we're going to show here. And this is the current method that's out there, ASTM D7918, which is a grease dye extrusion and sample preparation method, which creates a thin film on a substrate. And we have found that is in the same way the glass beads and the things that were done way back to try to get more thorough liquefaction, if you will, of the thickener, basically getting the thickener out of the way. Some of that is enhanced now by this thin film process, where the solvent can do a better job in agitation on the surface to break that down. And we've seen some good results with that. So the grease is on the thin film. That provides the better dissolution in the agitation. If we don't have that as an option, if you're doing grease analysis and you're not using the grease thief analyzer, you're just taking a little clump of grease or whatever, there may need to be some extra effort there to dissolve the grease and to isolate those particles. But and some of that's really going to be dependent on the chemistry of that grease. Some greases respond well to certain solvents, some do not, just based on their chemistries. And then also we see that as grease ages and gets degraded, it may be more difficult to get the grease out of the way for analytical ferrography. So we'll talk about that a little bit. Grease does need to be diluted with that grease-specific chemistry solvent prior to analysis. Fortunately, most of the greases that we process through our lab respond fairly well to a heptane toluene mixture that we use. As when you start with that thin film, it's pretty effective for a lot of grease chemistries. But now, once you do that, you've got to look at what about the wear that's there. And in oil analysis, we sometimes have to dilute that sample when the wear is real severe. My experience with grease analysis is that we tend to have more wear particles than we do in your typical oil sample. So the dilution comes into play more often to achieve this separation. Because, right, Ray, we don't want particles piling on top of each other too much and kind of hiding the story that's there.
That's correct. That's why you had that tilt that you see. I told you that was the air gap in between that you need to have.
Yeah. And if there's just too much there, it just becomes kind of a pile or a mound. And so by diluting it to 10 to 1, 100 to 1, we get to spread those things out even more, in addition to the tilt and so forth, so we can really see what's there. How big is it and what's there?
Yeah, and you just got to remember what your dilution factor is when you start comparing results to each other over a period of time. Okay, so that's the big key there.
We see that in practice by taking a little marker and writing right on the slide cover, the ferrography holder, if you will, what that dilution is. So that becomes at the forefront of the analyst's interpretation of what they see. And when you say, hey, there's a lot of this or a lot of that, there also needs to be this kind of qualitative assessment that factors in what that dilution really is, especially if this is something where we're following up a previous sample from the same equipment, and now we're into a dilution situation.
That's why your instrument's pretty good in terms of extracting the proper amount of grease from the closest to the wearing surfaces, so that when it does come out, we can weigh it or make sure you have the right weight and so forth. And then when you compare what's going on, then you can evaluate properly and what you see. Because nothing worse than making false claims. Because once you make a false indicator of what's going on, it blows up basically your how do I call it?
Your credibility.
Yeah, kind of.
Yeah, it can be that, or sometimes it even works to undermine the technology, right? People
Yeah,
say, "Hey, I
yeah,
tried that
yeah.
before.
It
I
didn't
did
work.
grease analysis,
Yeah,
and they didn't find this, or
right.
they said something was there and it wasn't, and
Yep,
it can be hard to recover from."
that's correct.
Yeah. So these special considerations for grease is that, I mentioned this. Sometimes greases have a much higher concentration of wear particles in oil samples just because they're cumulative, right? Between replenishments of grease, the particles are being generated. They're not settling out to the bottom. They're not being filtered out like you might have in oil. So there tends to be fairly high concentration in a lot of applications. And then you got some solvents that work well on most of your greases, and then this grease comes along and it's just not getting dissolved.
Yeah.
And you go and you make a slide and you look at it and you just can't see the particles. They're hidden behind clumps of grease or clumps of thickener, and that can be a problem. And I said about aged greases or stressed greases may be more difficult to dissolve than a grease that hasn't undergone those same kind of really changes, sometimes oxidative type changes. Um, then you might have mixed greases, and we find this a lot of times where there's just two different products ended up in the same bearing housing, and now here comes that sample, and how do you dissolve the mixture? Maybe one solvent would work well on one and not the other. So again, another challenge. One of the things that we've been doing is almost a secondary ferrous step here, and that is to use a magnet when you first dissolve the grease. Richard, do you have the chance to kind of show what our setup might look like? It's not too elaborate of a setup. We're basically taking the dissolved grease. So we've got the solvent in there. Our substrates will still be in there. Can you flip that over again, Richard, just to show that quick? And when you do that, you can see this. Just hold it up a little bit further. You can see the substrates, the plastic substrates, still in there, right? And so most of the grease has been taken off of there, but now you've got the solvent, the thickener, and the particles that are of interest. And so you can then, use a high magnetic strength magnet to kind of hold the particles to the bottom of that, and then allow the solvent and the thickener, but some of the non-ferrous particles too, to be washed away.
Yeah.
And so I think, Ray, that would be another situation that we would have to keep track of, that this is really going to be a very focused ferrous investigation where we're going to lose a good bit of the non-ferrous particles when they do that. But if we've seen that we've got a problem with even figuring out what's on the slide, this might be something that helps concentrate that ferrous wear for us. In the old method that you talked about, where you went into a different filtered oil and tried to get all that stuff out of the way, right?
Yep. Yep. That's one of the reasons why you had talked about types of particles. Well, what happens is we try to illustrate that first we want to categorize them as ferrous, non-ferrous contaminants, and then the types of particles underneath those three categories.
Mm-hmm.
That's what makes it much more I call pointed in regards to your I guess your recommendations or whatever you see in terms of the types of particles that are present. It's a cut, maybe a abrasive wear, but it's non-ferrous, or it's abrasive wear, but it's ferrous. And so now all of a sudden you're diagnosing exactly, okay, what's ferrous that I have in the system versus what's non-ferrous that I have in the system of the equipment that you're monitoring or your assets that you're monitoring. So those will makes it easier for you to pinpoint what's going on in a much more categoric format. So. Okay.
Yeah, in fact, we were just talking this morning in the lab. We had a customer send us some filters and asked us to categorize the particles that were landing on that filter, and we did just what you described. But sometimes it's hard to communicate that to the customer, to the asset owner. So we did create that flow chart. We went down and said ferrous and non-ferrous, and then within non-ferrous, what did we see there? What type of materials? What type of wear particles? Therefore, what type of wear modes, and so on the ferrous side as well. And then it just really helps you get to the point of understanding what is going on in this system. Correct. That's being captured in this, and it can be very helpful because we know this, it's really when you do ferrography, it's a partnership between the analyst and the asset owner. Yeah. The asset owner has a lot of the information about this this sample, about this, equipment that is really necessary to fully understand and comprehend what's seen in the lab, right?
Yep.
So it becomes, and so I was so fortunate when I started is that I was both, right?
Yeah,
I was the
that's
asset
correct.
owner,
Yep.
but the problem is I could only do so much in a day. And eventually we had to create, there still needs to be that communication to be effective where you can understand what's going on around that asset. What is its history? What's its metallurgy? How's it being operated? Has this ever happened before? And so on. And then from an analyst perspective, how much can we help this asset owner understand about what's in the particles that we found and make that connection back to, the asset's reality?
Well, the true nature of things is as becoming a predictive maintenance lab person, when you're taking on this type of technology, you really have to be a researcher first to research what is normal, abnormal, all kinds of different things. And you have to kind of play in a research mind frame. And then later on, you have to transition into what we call a production type mode on how to monitor what's going on. Because and the transition is, when do I do this? And that's what people get caught up in their underwear regarding to what's going on in that direction. Because you could be saying, okay, I got these 6 gearboxes or 15, 20 gearboxes, and I got to monitor these things. And so right away, you're trying to establish what's the baseline, what's all the different things that's needed to be involved with this, not only from a ferrography point of view, but possibly getting vibration information, possibly getting thermal information, possibly getting all these different bits and pieces of data, and then using that to say, okay, I've established what normal might be. Anything out of that ordinary, then I can now indicate what is abnormal, and I have records of that maybe, and then let that be your barometer of what's going on. So that's how you have to look at and approach things when it comes to certain, how do I call it, assets. Because a lot of the times the plant people won't give you any information. They won't cooperate with you. They rather, because they feel like you're overseeing what they're doing, and that's where it gets a little tougher on what's going on.
But if you can break down those barriers and you can communicate back and forth, the value of this process is so much.
Yes.
Yeah.
It's skyrockets.
Absolutely. I remember one of the first ferrography conferences that I attended, and there was someone volunteered to be at the front of the room and look at slides that people had brought.
Yes.
And, so we had an expert in the front of the room, and then we had, slugs like me who were, from the plant bringing in some samples and saying, I made this slide. Right. And I remember that, the one guy, he went through and said, yes, what we see here is this kind of particle, and it's a babbitt bearing, and that babbitt bearing is failing, and so on. And then the guy who brought the sample said, yeah, but there's no babbitt in that gearbox.
Exactly.
So, and to me, it just underscored that importance of being able to bridge that gap, to understand what's happening with the asset, to really get the most value out of analytical ferrography.
That's absolutely correct. And there is situations where you'll see things on the slide, and the people will swear up and down that it's not from the gearbox, and come to find out it's the copper line that's flowing the oil into the gearbox that got cut into by the mix shift of the gears themselves. Right. And they go, oh, my bad, I'm sorry, I didn't realize that occurred. But they were swearing up and down there was no bronze or copper alloy in the gearbox. So you can only talk about what you see on the slide. So
sure. Yep. So there's a lot of information in the materials that I put together for today, and for anybody that sees this and wants to see these, I'll share them with you. I'm not going to go through everything, but I will show a few of these slides, because I do want to get to Richard showing us some of the slides live, and then give Ray a chance to comment on some of them. But you can see some of like the magnetic lines of force here. Okay, up and down in the arrangement of the slide, telling us these are ferrous particles. Non-ferrous particles are going to be more randomly oriented and distributed around. So that's one thing we look for, is the magnetism effects. And then, we pulled some materials here from our LLA training classes, our ICML laboratory lubricant analyst, which does go into, identifying the wear mechanisms, especially in level 2. Abrasive, adhesive, corrosive wear, fatigue wear, cavitation, fretting wear, erosive wear. These are all different mechanisms that we might be trying to pin down when we look at our analytical ferrography slide. Abrasive cutting wear mechanisms are going to be described as both two-body and three-body. Here's a great big two-body wear particle. It's very wide relative to the length. It's several microns wide. It might look a little like what comes out of an ice cream scoop when you scoop it down through, your gallon of ice cream you sit down with every evening. And then it might get little cuts on the edge as well. And this can be due to the contact of asperities, surfaces, cracks or breaks, kind of one surface digging into the other and making this large two-body type wear. You also get abrasive or cutting wear mechanisms that are described as three-body, and they're more fine or wire-like, and they'll be very curly, and you can see this much different ratio of this particle here on the left that is maybe only a micron or two wide, which corresponds to the tip of a silica particle, a dust or a dirt particle being forced down into that surface almost like a tool bit and cutting and digging it out. You may even get crazy like this where you would swear this was what came out of your drill bit after you tried to drill a hole in a piece of steel, right? But no, this is microscopic. So it's essentially happening at that microscopic level and primarily due to abrasives in the lubricant. And then you get sliding wear, the kind of larger particles where you get kind of long or you get lines on there. It's a thicker particle, but you see lines or what we call striation where they are kind of rubbing one surface against the other. And they might be kind of rough or jagged. They may even have oxidation. They might change color because of the temperatures that are subjected to as this mechanism is forming these larger particles. Now, here's kind of a nasty one where you've got, these various lines, almost like the particles coming out, but the direction of contact is not in the same direction. It's a little counter to that. These are generally thought of as particles bigger than 15 microns. That's kind of our cutoff between normal, although there are some small particles that we wouldn't want to call normal, but that's generally that trade-off to where we get into the severe wear mode of these larger size particles. And we'll show some of these, Richard will, when we put the microscope up.
Go back to the last slide.
Yeah, sure, Ray.
Number 16. There's a point that needs to be made. These are application dependent, okay? Because when you start thinking about a drag line out in Wyoming, okay? I don't know if anybody is international, but there's surface mining. These drag lines are huge. And when they talk about a bucket, the bucket is probably as big as the building here, or half the size, or big as the office that might be in here. And the particles that is in the 8 to 10 microns are nothing. Particles into 200, 300 microns, that's when their cause and effect will come into play for adhesion wear mechanisms for them. So I just wanted to mention that it's application dependent, whereas the complete opposite in a turbine world, where you have no touching of anything, and you start seeing particles of 15, 20 microns, that's detrimental to that application. So I just wanted to point that out to people.
That's a great point. And sometimes, Ray, you see that in the difference between, say, a turbine bearing versus a gearbox, right?
Yes,
just like the
correct.
type of component it is tends to generate different sizes, and your action levels have to be adjusted accordingly, right?
That is correct. That is absolutely correct. That's why we just use 15 to 20 microns as a layman's average of what might be an issue in terms of abnormal for wear debris.
It's like a starting point, but then you need to factor in what is this application?
That's correct.
What is the
Okay. So
what type of mechanism and so on. Here's the other end of the scale, right? The corrosion wear mechanisms where you might be hard pressed to actually come up with a measurement. It might be so small you almost don't even make the particle out.
That is correct. And typically that's at the exit end of the ferrograph, not at the entry where it first starts in terms of what's going on. So
because they're so small, they stay in suspension longer and finally get pulled out of the slide. But these might be submicron. They may just look like a blanket of material, but it really is these tiny, tiny particles. And knowing that that's the wear mechanism is really important in knowing what to do next, right?
Yeah, that's correct. That's correct.
And then you got fatigue wear. They might be normal rubbing wear, but some, like Ray says, depending on application, some wear is expected. But large quantities or large sizes are the things that trigger us to say, hey, something has changed here, and this is abnormal, and it needs to be addressed. Here's some fatigue platelets or laminar wear particles, like you see here on the right. And then we've got a smaller sphere here on the left that kind of looks like a donut shape or a tire shape. The spheres get generated in the bearing fatigue cracks. And sometimes they'll show up early in the process, maybe even before you see the spalling or laminar wear, but very, very small spheres. But then we get into the larger laminar wear particles where these are just coming up off of that surface due to the subsurface cracks that have formed. And they may be so small you can see right through them in spots, right?
Yeah.
You can see that. And I should say that most of the pictures we're showing here, and maybe we'll start on the microscope with the green transmitted filter in place. And then you see that green light coming up, and it helps you pick out the edges of the particle. But when you see the green in the middle somewhere, then it's like, well, yeah, I'm seeing right through it, right? So I've got a hole in there. It's so thin, a micron or less, that actually you get holes in those particles as they form up. There's some more spheres, and the spheres can be from cavitation. They can be that early sign of, if they're real small, they can be that early sign of fatigue, but they can also be due to contaminants, right, Ray?
Yeah, that is correct. When you see like welding and grinding, you see these sparks that fall off of the thing. Typically, the eye can see 40 microns. So when you start seeing spheres that's in the 40, 50 micron range, then you know it might be coming from, say, the 55-gallon drum container, or or it could be a process where you're in the automotive industry, and all the welding that's going on in the automotive industry falls right back into the hydraulic fluid that's basically responsible for the fluid for the robot, that arm that's involved with the welding apparatus. So
especially if you don't like have a good breather system,
correct,
or seals and that sort of thing.
That's correct. That's where all those type of things come into play.
So it talks about some steps, starting at 100 and so forth, and we'll do that with Richard here in a moment. And we'll look at some of these details and so on. Well, we talk here a little bit about using polarized light. We can look at polarized light as well. We can put cross polarizers in and identify some particles relative to others, whether they appear in these cross polarizers, either from a transmitted or reflected standpoint. And we talked about getting some customer feedback. The heat treatment can help us further narrow down some metallurgies, some possibilities, not specific metallurgies, but things like high alloy, low alloy, stainless steel, non-steel, these kind of things, and that can help us too, using the heat treating to figure them out. We talked about the transmitted and reflected light. And you see here we've got the green light coming up from both of these, but you see the red. We put a red filter here on the left, and that's showing us that that's unoxidized metal there that's shining that red filter back towards us again, helping us determine metals from non-metals and that sort of thing.
Yeah, the beauty of the bichromatic microscope is tendency is if you're going in production mode, you want to know what is metal from non-metal, and then work on your way backwards from that. What type of metal you might have, what type of non-material that you have, a non-metal material. Mm-hmm. So those are the two basically walks of directions that you might want to go, and that's due to turning off and on the light from both the bottom and from the top. We just have a fancy name for it: transmitted light and reflected light. Reflected light is for doing a lot of what they call metallurgical studies. Transmitted light is used for biological activities. So those two aspects are combined in order to be able to pinpoint exactly what type of situation you have in terms of the metals material that you have on the slide. So just throwing that out there.
Yeah, in addition to using filters, which you can see the color contrast, sometimes it's just best to turn one off, right? And
Yeah.
just look at the slide with just transmitted light or just reflected light and see what story that tells you too.
And at higher magnification, because you can look at a slide that's 100x, and then it looks like all dark metallic oxides, and then you go to a 500 to 1,000. You go, wait a minute, these particles are all shiny. They're just on a different angle, giving basically less light back into your eye. That's why you're not able to see it, and that's where on your microscope you have what they call NA, numerical apertures, in terms of what can be absorbed, what angles can be absorbed on the lens, those type of things. And remember, these are close working distance lens. So if you have stuff that's building up, obviously you don't want it being interfered into the microscope lens itself. So those are some of the things you have to be careful of when you start looking through the microscope in this direction. So
that's why we start up at 100 to get our focus and then bring the other objectives in.
Absolutely. Absolutely.
And make sure you don't crank it in the wrong direction.
Or you ruin an $8,000 lens or a $6,000 lens right off the bat. And that's what you don't want to do. Okay.
And Ray, I think there is potentially the risk here of going a little too fast when you're looking at a ferrography slide sometimes and just missing out on some of the detail that's there, right? If you don't take the time to turn the lights on and off and compare the reflected to the transmitted, to try the different the filters and even the heat treating process. I think a lot of times that's looked past, right? I think you're a big proponent of heat treating.
All the time, as much as possible, because it changes things. What I haven't done lately is gone to a higher temperature of heat treat to see what goes on there. Now, the one other aspect of that is, let's not think about it from a ferrogram point of view. Let's think about it from a patch test or whatever. You could change the element or the material color on the patch if you have a what I call heat resistant patch in that direction. And I'm working on those things with ASTM in that direction. So that's a good thing that I'm looking forward to. So it's just a matter of pinpointing what's going on. So
yeah, that's some exciting work you're doing with the patch, especially when we want to understand some of the heat effects on some of the non-metals and things that you can, and then some of the non-ferrous, when you really want to try to get them captured for sure, and then see what happens when you heat treat them. So I think that's some great work you're doing there.
Yeah. And hopefully we'll come to fruition with that one for sure. So.
Yep. So I want to, and here's some, and you talked about the first temperature there, the 330 temperature, which is what a lot of folks are doing. But, I think this is something to think about, especially for folks who might be the asset owners and they're trying to learn today what they can about analytical ferrography and what they should be able to learn from it. And sometimes, you'll get an inquiry and someone will say, well, how much does it cost to do analytical ferrography? Because, they want to compare that to somebody else threw a price out for them or something.
Right.
And what I'll say is it's not all the same, right? There's the level of experience of the analyst. There is the level of detail that goes into ferrography. But just if you would think about it, what would be the cost of looking at the slide one time versus looking at the slide twice after you've heat treated it? It's going to have to, it's going to take more time for somebody to do that. And therefore, you might not be getting apples to apples when you think about it. So so much, in my opinion, there's so much to unlock from analytical ferrography when the other indications of testing say it's time to do that it might not be time to cut corners and whatnot, because you could be leaving a lot of information on the table if you rush through it.
Yeah. Well, the time you're getting to analytical ferrography, you have a problem. It's just a matter of what is the problem. And so you tend to be in what I call research mode versus production mode. Some people want to be able to just run an analytical ferrography, just say, okay, I kind of have evidence of what that might be. I think I still have 6 months left on the unit. So that decision for the asset means continue as usual, because guess what? The company wants production going out the door as much as I can, because they might be, for instance, I'll use an example. They might be a plant that has what we call sweet potatoes. Sweet potatoes are a big deal in the summertime, and then they shut the plant down after July, August, and all they're doing is shipping all these sweet potatoes so they'd be ready for Thanksgiving, for an American holiday, that type of thing. And next 6 months, they're just cleaning up the equipment and trying to repair all the things because they force themselves to be able to still do things within that 6 month period. So didn't mean to take up too much of your time. Why don't we go ahead and...
Not a problem, but I'd like to get Richard on here with the slides, and so I'm going to turn my camera off.
Do I turn mine off too?
Well, you can leave it on. I thought it could give us more of a display here. What I need to do is close the slides so that Richard gets a bigger view on the screen here, and I think we're seeing that with him now.
I see that.
Okay. So we're live, Richard, right? So what are you going to show? What are you going to show us here? Where should we start?
So why don't we start with some of the 2 and 3 body wear?
Great, good choice. Do you have any background on? Was this a grease sample slide or oil? Do you remember on this one?
This is a grease sample.
Okay.
And this is, I'll get it in focus here. It's right at the entry. This is at 100x. Kind of hard to see, but you can pick out a couple of the cutting wear particles right here.
Okay.
Some small ones in here. When we get, I'll zoom in, go to 500x. It'll become much more prevalent for everybody.
Is this before heat treatment?
Yep.
Okay, good enough. Yep.
So turn up the reflected light.
Transmitted,
yeah.
Yep.
Yeah, and you're using a green filter and transmitted.
Yep. So here we can see some of those nice cutting particles. We got.
And do we call that 2 body or 3 body? Do we see any abrasive material, contaminants?
On some of the thicker ones, so kind of like right here.
Yep.
And this bigger guy would be our 2 body. And then we've got some a little bit harder in focus, but this one right here and this one are a little thinner.
Mm-hmm.
And they're the ones that, like Rich mentioned earlier, they look more like hair.
Right.
And those are our 3 body. And then I can.
I think one thing, Richard, is I can see here is there's some particles that you can see, they look green, right? That means they're transmitting light, and those have to be some of the crystalline particles, and they could be the culprit here for some of the 3 body.
What you can do if you have the polarized filter, they will illuminate the crystalline debris that you may be sitting there. More so at say the reflective light, not the transmitted.
But what I will say, what I know is that while you can pick them up in the eyepiece, they don't get enough light into the camera. So I wouldn't try right now, Richard. It's going to be hard to show that specifically. But yeah, this is so when Richard said we've got a nice slide with some nice particles. That's a ferrographer talking. That's not the asset owner talking. The asset owner is not going to think any of this looks nice.
No. And in fact, the asset owner probably will do another thing is if he's getting a lot of these cutting wear or abrasive wear, he might want to say, "Is my vibration indicator doing anything?" Because if I have a lot of misalignment components going into play microscopically, I should get some sort of signal that indicates it's not running at its normal level. And if that helps to pinpoint what's going on, and then he might say, what's the thermal guys thinking? Is it too early? Is it too late? If I'm starting to generate heat like I shouldn't be, then all 3 of those then would indicate they can plan for what they need to do next. And that is create a certain shutdown window to make the certain changes within the components so that they don't have to worry about an emergency shutdown, but they have to pay people triple overtime and so forth and so on. So,
yeah, the 3 body, you kind of look at it, you look at your other oil indications. Well, you look for particles here like we did, like for the crystalline particles.
Correct.
You also look at your particle count and other things, and then you talk to your asset owner about, what are you filtering? Do you filter your new oil? Or if this is grease, right? So we asked the question, do you know what the cleanliness of the grease is? And, is clean grease going into your grease guns and so forth? But you're right, Ray, when it gets to 2 body, it might be highly thrusted, right? And that
Yeah.
could be creating the interface of that one surface to gouge into the other,
Yep.
or it might be a misalignment condition. So that's really where this goes together nicely to help us understand what we should do next, right? To your point, is this something we need to act on now? Can we get to the 6-month outage that's coming up, or what have you? So, Richard, let's look for something else. You had some spheres to show us, right?
Yep.
And this is all from grease applications, correct?
Yeah. We're going to share some greases here. Some look pretty good here, as you can see. Not a lot of interference, but I did also ask Richard to bring one up where the thickener was a bit of a bugger and makes it tricky to look at too.
Yep.
So we'll do that.
One thing I always tell customers in training is that we provide the ideal photo micrographs. Okay, they don't get to see the everyday type activity because it's boring. All right, and so I tell them not to get caught up what I call the jewelry effect of looking for something fantastic when that's not always the case. That 80% of the time, if you don't see anything, that's a good thing. Guess what? Your machinery is running well.
Yeah, that's right. Well, that's a big sphere there. Goodness. What do you at 500 magnification here, Richard? Or
Yep, that's correct.
Mm-hmm.
So we got in the middle, we got a couple of them in a line there.
Okay. All different sizes of spheres.
Yes,
Ray, what does
are.
that make you think of when you got big ones and real small spheres together?
That's the tough part. I don't know, to tell you the truth, when you start seeing large and small combined together. There are times I think, okay, it's got to be contamination if they're averaging 30 to 40 microns in size, and they're all going down in small areas. But I've seen things like this from, say, a little bit of a diesel application where it might be in a mixture of oil going in and it's also some wear situation going on at the simultaneously. So, you can have those type of issues, because when I see I see crystalline too in this stuff, and the background looks like almost like friction polymer too. So
yeah, it does.
so I'm seeing red oxides too. So I'm seeing a litany of different abnormal type wears. I don't even know the application other than just it's grease.
Well, one thing I'll say is that we know it's grease, and sometimes grease is like fly paper.
Okay. It catches stuff. Yeah.
It's throughout its life. I mean, from the time you pull, well, really from the factory, to be perfectly honest. Yeah. But from the time you open up that container and you're transferring and you're putting it in a grease gun, that's all opportunities for debris to get in there. It never gets a chance to settle out. So we do sometimes see these hodgepodge of particles that you almost have to put some of it to the side and say, there's some contamination in here. And you know what? Let's go back and get a sample of the grease right out of the tube, or the grease right out of the grease gun, and almost do a differential kind of analysis to say how dirty is the grease going in, and then let's look at the new particles that show up that are going to be about the wear situation in that machine.
And that's a wonderful way to do it, because what you're doing is you're putting the reference of the grease, new grease, against what's going on with the application, and then it's like almost doing a vibration where the vibration normal signal, say, is 106, and then the bad signal is 112, 115, that type of thing. So it's a differential of those two readings together. Now look at this. This is a hodgepodge of stuff, also with much more spheres, lots of spheres. I call that contamination for sure. So
Yeah, this one I do know. Previous employee followed through with the customer, and this was a motor that they had put in the repair shop, and somebody had been doing some grinding and other repair work next to it, and they contaminated this piece of equipment.
Yeah.
So it's like post use, right? It's the grease. This got into the grease after the machine had been running, which is pretty wild. So, these are all things that we need to factor in. Ray, I saw a question come in from Andrew.
Okay.
And Andrew asked about, can you use this to look for biological type material?
Well, what type? Because back in the late 70s, the inventor Vernon Westcott, used to do what we call synovial fluid in knee joints for horses, and so you can extract, but you have to use a certain chemical that associate with it. And I think he was using a mixture of alcohol and distilled water to be able to extract those particular materials, and then put them on the slides. I think one conference he brought in red blood cells to take a look at certain things, and then he was doing things what I call with cancer patients for breast cancer, but working with the Cleveland Clinic. So
Mm.
it's not like you can do biological, but you have to set up the magnet in such a way that it's not flowing the way you want it. It's flowing from a vertical position, not a
Oh,
horizontal position. So
okay.
because red blood cells has a lot of magnetism in it. Okay.
So that would be looking at biological fluids.
Yeah.
I'm thinking his question might have been about biological contamination into the lubricant, like microbes and things like
Oh,
that.
well, we used to have a magnetizing fluid, but we stopped that because of the mixture of the type of fluid that we're using can't be used today because of the cancer-causing agent that's involved. But it was involved with the methyl ethyl ketone and some other what do you call it, erbium salts. That's what help the magnetism for biological items that could be magnetized and then put on your substrates. So
Actually, Richard, did you respond to that question? What do you got for us here?
I didn't respond per se to the question, but this is just a historical sample where we found a bug. So the bug is kind of decomposed. Right here, you can see the legs.
You're kidding me.
Nope, this is its head, and then this is the other side of the legs. So like this is a customer where they had a issue with
actual bugs
in the facility, and then the bugs were getting into the equipment.
Wow.
And contaminating the grease. And then we were seeing they were so small that they were able to go through the ferrogram maker and lay on the slide.
That's so this was like food processing or something?
Nah.
I don't think it was I think it was just a manufacturing facility. I don't think they were making food.
Okay, we won't talk about who the customer was.
Yeah. No.
You won't eat that anymore.
Hey, Richard, can we show one more here? And as we get to the end of our time that we've got allotted today, I think we got to do a follow-up to this because I think Ray and I could riff on this for a long time. And hopefully this has been of value. And I just feel like we're scratching the surface, Ray.
You just let me know. Give me a couple-week warning. And make sure it fits into my schedule. I'll come back, okay? For sure.
All right, well, good. Let's give folks one more here to look at. Richard, what are you showing us?
So here we got one with just a lot of red oxides. Let me get that in focus for you guys. And then you'll also notice there's a little bit of, if I turn the reflective light up, it almost looks like white. And that's the grease thickener effect. Yep. So sometimes we do have to keep our transmitted light low to not get the thickener to shine. But this is just an excessive amount of red oxides on this slide.
Which refers to water in the oil. That's all.
Maybe. Yeah, some of it looks like scale, like bigger particles, but some of it some of them are fairly small and kind of chunky crystalline, aren't they, Richard?
Yeah, I'll go into
uniform.
I'll go to 500 and we can kind of check them out a lot better.
Yeah. Now I've seen this white thickener thing in some greases from, say, the steel industry. And what happens is the customer showed me a photo micrograph of it, and then after heat treatment, it melted. It disappeared.
Yeah.
So there's where the heat treating aspect. So we knew it was a lubricant situation with an additive package that came into play.
Right.
And so that's how we're able to pinpoint what's going on, because we wanted to make sure that white crystalline product that we thought was not a permanent product that goes in and start messing around the asset in many different ways. So
that's great. And you throwing one last one in there, Richard?
Yeah, a little low alloy steel.
Yes, I just thought this was a really nice one to show the effects of magnetism, where it gets those particles to line up.
Yep.
And then, as Ray pointed out, we've got the slide's been heat treated, and due to that blue color change, we know we've got quite a bit of low alloy steel
and some what I call case hardened steel. That's the brownish or purplish type color. The thing that someone doesn't teach sometimes is when you when you look at heat treated particles, you try not to have the green contrasting filter behind it. Notice you're trying to use the white light instead so that you can have a good contrast with the blue color. What happens is green tends to blend into the blue, and so it doesn't give a good contrast of what the particles shapes and sizes are when you get to higher magnifications. So that's one of the reasons why you may see photomicrographs with a lot of what I call gray background, which is really truly the white transmitted light, not green transmitted light. Okay,
Just to pull up so you really see what the true colors are
that's correct.
rather than being influenced by
Correct.
that filter in there. Yeah.
Uh,
Great.
yeah, last thing I want to say is you got to remember, you are showing highlights of the story of what's going on with this particular with this particular asset. And if you don't make it a wow type thing, guess what? The manager of the plant or anything will do nothing and say, okay, all right, that's good, and then move on to something else. So you have to make an impact in your imagery. That's why companies love to see the what do you call them, the I can't believe I can't remember the thought, with the heat guns,
Thermograms, infrared thermography. Yeah.
thermography. Yes, they love to see that thermography picture one against the other. So this is just another way of possibly showing those type of things in regards to the type of wear that you see. And once you explain that to the asset owner, he says, "Oh shoot, you mean my metal is abrading away my gearbox? We got to do something." So that's kind of what he has to look at. So
you want to tell the story that elicits the right response, right?
Correct. That is correct.
Yeah. Yeah, I used to do infrared thermography, and if I knew that some action needed to be taken, there was a lot of red and yellow in the picture, and if there wasn't, it was a lot of blue and green. And I might be at 100 power magnification or 800, depending on the response that needs to be elicited. But to a certain extent, we want to try to be consistent as well, so that the right decision and comparison can be made. But you're right, we want to be able to tell that story and have an impact, and more than just a page full of numbers. And that's what analytical ferrography really does for us. It brings that, as they used to call it when I started out, give me some pretty pictures. And this is obvious. Well, to my eyes, this is a beautiful one.
Yeah, it is.
So,
it is it's called the proof of the pudding. That's what we used to say. You got to have some kind of proof that, because you can't lie about there's particles wearing away, because I see it. I have it right there. I have photographic proof of this. That type of thing. So
that's great. Well, Richard, thank you for walking us through this and showing us some great slides that you've made here, and thank you to Ray Dally for joining us today on our Grease Thief Thursday. Ray, it was great to see you again, to work with you again, and to have your insight and knowledge and input. And I hope we can get you back on one of these in the future.
I think I can make some arrangements for it, probably in a couple of weeks or so. Okay.
All right. Super. Well, that ends for today. Marissa, you got us lined up for next week and what's coming for the next Grease Thief Thursdays?
Yeah, absolutely. Next week, we have talking about wind turbines. So that's exciting. Then after that, we're talking about MOVs. And then after that, we might also do some biological contamination and talking about ATP. So we got some good things lined up for you.
Okay, that MOVs is motor operated valves, which might be of interest to folks in the nuclear power industry, maybe petrochemical for sure. So, well, again, thank you. Thanks for Marissa and Richard, and thanks to Ray Dally for joining us today. And we'll see you again next week.
My pleasure. Take care and have a good day. And most of all, everybody stay safe. Okay.
Thanks, Ray.